and see whether it works now. Okay.
Yes, the screen is visible.
Okay. Now you can see.
Yes, sir.
Yes, sir.
Okay. Okay. Great. Okay. Okay. So I think we were here. History. Were you able to, or should I go
Yes,
back
sir.
one more slide? Okay. So as we were saying, that Fleming discovered penicillium growing in a petri dish way back in 1928. Although it was called Penicillium notatum, as of today, when people go back and analyze what had happened, they realize that that was named incorrectly. It is now called as Penicillium rubens. Okay, and later, Flory, Chain, and other co-workers isolated penicillin from this mold and showed that it had antibacterial effect. And about 10 years later, 10 to 12 years later, it was introduced as a antibacterial for general use by the public, and it saved millions of lives in the World War. Okay, this is how it looks. Okay, this is Penicillium notatum, and this is Penicillium chrysogenum. Okay, now if you were to look at the way penicillin was made, in the first when they started making penicillin, because this is a mold which grows, with a lot of mycelia and hyphae, they actually started producing it using a surface culture. So they had a medium on which penicillin mold would grow. The hyphae would go into the medium, and they would utilize the nutrients, and they would produce penicillin and release it into the medium, and they would extract it from that liquid. But this was fairly inefficient. So after a while, they started investigating whether they can grow it under the surface. That is what is called a submerged culture. Okay, and some other variants of penicillium species had the ability to grow in the medium and also produce penicillin. Okay, so as of today, the method which is used for producing penicillin is what is called a submerged culture method. Okay, so as I said, in surface culture, you use a liquid medium without agitation, where the fungus grows on the surface, and then extract the penicillin from the medium on which it is growing. As opposed to that, in submerged culture, the fungus will grow in the liquid, which is vigorously aerated and agitated. And after incubation period, you wait for the penicillin content to become high in the liquid. Then you separate the organism from the medium, and you extract the penicillin from the medium. Okay, so as of today, penicillin is produced by this submerged method, as it is called. Okay, now the organism which is used for industrial production of penicillin is a Penicillium chrysogenum. But if you were to try and look at the literature and find out which exact penicillium strain they are using and whether you can get it, you'll find little to no luck in getting that information. And the reason is, most of the companies which are in the business of making penicillin will never actually tell you exactly what they are using, because it's kind of like a trade secret. Okay, the last thing they want is to tell you how they got it, where they got it, and also to give you a sample of it. Okay, they will never do that. Okay, but if you look at the history in terms of some things which appear in the public domain, you will realize that the original strain, was called as NRRL 1951. Okay, the NRRL stands for Northern Regional Research Laboratories. Okay, and 1951 is probably the year in which they produced this very high yielding strain. Then later on, that was modified by doing mutations like strain optimization to give a little tag there called B25. Okay, and then from this, one of the strains was developed, which was called P2NIAD18, which was used by Pan Labs to produce penicillin. Also, this was the origin of another strain which was called as X1612, probably produced by X-ray mutation, and that was used by SmithKline Beecham Pharmaceuticals. What nowadays is called as Welcome. This company is very interesting. It was called SmithKline French at one time. Then it is bought over by Glaxo. It was called GlaxoKline, and now it is called Glaxo. And it went through a name where it is called Beecham Pharmaceuticals and stuff like that. Okay. So basically now Glaxo is the big company under which all of these come, and they produce a strain which they call B1952 from this X1612, and that's what they use. Okay, that's what the evidence says. And one of the strains which was developed by using UV and nitrogen mustards and stuff like that, and sulfur mustard was ASP78, which was used in Spain. Okay, and then from that was derived something called as Wisconsin 5412SS and so on, and then this strain DS is used in Netherlands. Okay, so we really don't know what these strains are. Okay, except the fact that they all exist, and different companies guard it with uh, with a lot of jealousy so that it never falls into anybody's hands. Okay, and as I was telling you, it has gone through different names. It was initially called Notatum, then Rubrum, now it is called Rubens, and then you have this one which is penicillin chrysogen. Okay. Now, typically, what you'll find is the way you produce penicillin on a large scale. Okay, uh, is by doing what is called as a starting with a starter culture. Okay, which means you start it in a very small way. You take a little, actually speaking, a loop full of culture and put it in a small, conical flask containing about 100 to 200 ml of medium, and you start growing this fungus in there. Okay, and after it starts growing there, then put it on, make it on a larger and larger scale, and later on, when it's enough liquid is there, you then inoculate the big fermenter. Okay, now you have to remember that these fermenters are 50,000 liters. Okay, so if I want to inoculate 50,000 liters, no, typically I need to put 5,000 liters. To inoculate 5,000 liters, I need what is called as 10% of that. Okay, so as I said, 50,000 liters, 10% of that is how much? 50,000 liters ka 10%. 5,000 liters. Then you have 500 liters. Then you have 50 liters. Then you have 5 liters. Then you have zero point 0.5 liters, which is 500 ml, which is 50 ml. So you can see how you can start, right? You start with a small 50 ml flask. You put it into something which will give you 500 ml. Then you put that into something which will give you 5 liters. You put that something into 50 liters, and slowly build it up. And then when you reach a point where you have 5,000 liters, then you put it in this big tank which is for 50,000 liters, and that's when the actual fermentation begins. Okay, so this process of starting from lyophilized spores, which might be in a little tube, to putting it on a slant and then building it up, is called as a fermentation chain or fermentation trolley, as it is called. Because if I take lyophilized spores and put it in this big fermenter, no, I'll have to wait for many days and keep on stirring it till there is enough fungus so that I can get penicillin. So there will be a lot of wastage of power and resources. So I slowly build it up and then I add it to the big fermenter. Okay, so that is the idea. Okay, now as I do this, you have to remember that I need to add a lot of things also. Okay, I need to add, I have to maintain temperature, pH, aeration, but I need to make sure that there is all the things which are required for the growth of the organisms. Okay, and that includes carbon source, nitrogen source, a mineral source, other precursors which are needed for production of penicillin, and antifoam agents. Okay, and typically the carbon source is lactose. Nitrogen source is sometimes ammonium nitrate, or sometimes they'll also put corn steep liquor. Other carbohydrates like glucose and sucrose may also be added. And sometimes instead of adding pure sources like this, some fermentation companies also use molasses, which is kind of a crude way of getting carbohydrates, or you can give soya meal. Okay, and then as I said, for a nitrogen source, you can use ammonium salts like ammonium sulfate, or sometimes you can use corn liquor. Then you add a lot of these salts like uh, you know uh, sodium phosphate, potassium phosphate, sodium sulfate, magnesium sulfate, zinc chloride, iron sulfate, so that you get all of these other elements which are needed for the growth of the organism. Okay, and then, as I said, when you want to make very specific penicillin, you add very specific precursors. For example, if I put phenylacetic acid, then that is a side chain which is attached to that nitrogen, so I'll get a lot of penicillin G. If I put hydroxyphenylacetic acid, then I'll get penicillin X, okay, and so on and so forth. Then I put phenoxyacetic acid, I'll get penicillin V, okay, and therefore, hello, yeah. So what happens is, depending on the precursor that you put, you'll get very specific penicillins which are produced in larger yields, okay. And as the fermentation goes on, it will start forming. So you have to put lard oil or octadecanol or silicones to prevent foaming. Okay, usually what you do is you follow the fermentation, and when what happens is all the components of the medium start to get used up, the pH starts to rise, okay, and it starts to become more and more basic. And usually sometimes just before it hits pH 8, the fermentation is stopped, okay. Uh, and okay, and then once you stop the fermentation, then very systematically you first remove the organism, which is Penicillium chrysogenium strain which you are using by usually filtration or straining, and then you extract the penicillin from the main medium. Okay, and this is how it is done. Okay, so the first thing I do is, after I finish the fermentation, I centrifuge the liquid. So when I centrifuge the liquid, what will happen? Because the mycelium and other solids are got high density, will all become, they will precipitate and become a little plug at the bottom of the what you call a container. Then I can simply decant the supernatant and be free of the mycelium. And now something very interesting is done. That entire fermentation medium, which has got penicillin in it, is made acidic, and the pH is brought down to about 2 to 2.5. Okay, and the reason they do this is because of the structure of penicillin. Okay, so if you look at the structure of penicillin, there's an acid here. Now, if I make the pH basic, this will be ionized, and when this is ionized, the solubility of penicillin in water will be higher than the solubility of penicillin in organic solvents. However, if I make the pH acidic, then what will happen? This carboxylic acid group will remain in this unionized form. And when it is in the unionized form, its solubility in water will decrease, while its solubility in organic solvents will increase. Okay, and it is that principle which is used for extraction of penicillin. So when I take the fermentation broth and I make the pH 2 to 2.5, then basically all of the penicillin is present in the unionized form, or in what is called a COOH form. And now what I do is I extract it with organic solvents like amyl acetate or butyl acetate or methyl isobutyl ketones. Okay, and when I do this, most of the penicillin will now come into the organic layer. And once it comes to the organic layer, I separate the organic layer, and now I do something very interesting. I take this organic layer and I re-extract the organic layer with what is called as basic water. Okay, adequate amount of what is called as potassium or sodium hydroxide in the water. Now the idea of doing this is, when water is added to organic solvent and the organic solvent water layer is what you call immiscible, and the water layer is basic, what will happen is, as you mix the two, as you shake the two, some of the penicillin which goes into the water layer will be ionized and will be trapped in the water layer as the sodium or potassium salt. And because of this, more and more penicillin will end up in the water layer, because the solubility in the water layer is much better than the organic layer now, because I've got potassium hydroxide or sodium hydroxide. And in the ionized form, it has got much higher affinity for the water layer. Okay, so what I do is basically back extract the penicillin into the basic water layer. And then what I do is, again, in order to purify things, I take that basic water layer and make it acidic again by adding acid. So when I do that, what will happen? Again, the penicillin will become unionized. And then when I add organic solvent, it will go back into the organic solvent. Now, I usually do this 2 or 3 times because when I do this many times, the penicillin I get will become purer and purer because other compounds will start to get now eliminated. Usually, finally, in the final step, what is done is from the organic layer, penicillin is extracted into NaOH solution, and then this NaOH solution is slowly heated or what is called as subject to vacuum evaporation of water and made concentrated. Now, as it gets concentrated, you will suddenly find that even the solubility of penicillin in this concentrated water starts to go down, and it will start precipitating as a sodium salt or potassium salt, depending on what you add. Okay, and this crystalline penicillin salts, what you call sodium penicillin or potassium penicillin, are then washed and dried, and then other treatment to remove pyrogens, etc., or sterilization if needed is done, and then it is used for making the penicillin tablets, penicillin capsule, penicillin injections, whatever, penicillin ointments, and so on and so forth. Okay, and that is how we get at penicillin. Okay, on the industrial scale. Okay, now in your syllabus, they also have that we should be teaching a little bit about how we produce other things like streptomycin and vitamin B12 and dextran. Okay, and what I'm going to do is and leave that little bit for self-study and see if you as a class can find information on how people produce something like tetracycline or streptomycin, vitamin B12, dextran. Okay, remember last time also I gave a little project to your class, divided it into like groups. So they do the same thing. You have the same groups, right? Make 4 groups. One of them will do gather information about tetracycline production by fermentation. Another one will do, the second group will do streptomycin. Third group will do dextran production. Fourth group can do vitamin B12. Okay. And the fifth group, and I'm going to give you an interesting project here, we'll look at literature to see how they produce single cell protein. Okay. But this you can give me, about 2 weeks from now after the exam and all. Okay. Uh, so at the moment, I'm going to stop here so that hopefully I've given you a feel for, how these large scale fermentations are done. How do these fermenters look? And I give you one example of how they produce penicillin industrially. Okay. Now remember, again, just as I told you, these are all industrially produced things, and information about exactly how things are done will be very difficult to get. Okay. Although people will suggest that this is how it is done, in the real world, the companies will never quite tell you exactly how they do. So they'll never tell you exactly what is the pH. They'll never tell you exactly how much is the solvent, which solvent they use, how much they use, whether they use mixtures. They'll not tell you what is the pH of this sodium and potassium hydroxide. They'll just give general things. This is how we do. This is how we do. And usually, when you try to do it, you'll get penicillin, but it'll never be as efficient as their processes. Okay, because they guard these processes because they're secrets. Okay, so I'm going to stop sharing here, and I'm going to go back to the main screen. Okay, and I'll leave it open for questions. Okay. Now, if somebody had put something in the chat box because I logged off and logged back again, the previous question which was in the chat box is now gone. So if you have a question, no, you put it again in the chat box or you unmute and ask me. Okay, and that's the only way we'll be able to get at it. Okay, so any questions at this point? Anyone?
Hello, sir.
Yeah, yeah.
So, while we are extracting a penicillin,
Mm-hmm.
so ultimately we are taking the penicillin in aqueous media itself, right? Which is like when penicillin is ionized. Like we have
Correct,
penicillin in the organic layer, and then we are adding sodium
correct,
hydroxide, so it's getting ionized and it's forming a salt.
correct, correct,
So, like eventually in the end, you are getting a salt only, right? So why we are
correct.
extracting it in the organic layer first and then again in the aqueous layer?
See, when you do the fermentation, no, uh, in the fermentation, you're adding things like molasses, you're adding corn steep liquor, we are adding, lactose, glucose, a lot of mineral salts. Okay, sometimes the people also add vitamins. Sometimes they'll add things like yeast extract. And remember, in this mold is growing, and mold itself also produces a lot of things. So in the end, in that big medium that you have, in which there is penicillin, there is also a lot of other things. Okay, in addition to penicillin. Okay, for example, if I were to take the medium and directly extract it with water, which contained sodium salt or potassium hydroxide, I will not be able to, because remember, the medium is also aqueous, and what I'm trying to get it into is also water. So they'll just simply mix. All I will get is that the entire medium will become basic. So in order to avoid that, what I do is first make the medium acidic. Okay, when I make the medium acidic, everything which is acidic in nature will now be unionized. Okay, in addition to my penicillin. So when I take this and extract it into organic, it is not that I'll get only penicillin. I'll also get every other compound which is a weak acid and which is now unionized. It will all come into the organic layer. Now, when it all comes into the organic layer, in addition to these weak acids, also things which are generally lipophilic will also come into the organic layer, like fats and all. Now I take this organic layer and I back extract it with what is called as basic water. Now when I do that, all the lipids, okay, or all the fats which are in the organic layer will stay behind, because they are not compounds which are weak acids which will now get ionized in basic pH. So they'll just go away in the organic. And now what will happen is I'll start getting a lot of things back into the water layer, which are actually weak acids, which are now ionized and into the present in the water layer. Now, as I do this, what will happen is some entities which are forming like a suspension, when I do this extraction, they'll also start coming with the water layer. So my water layer is now also not clean. It has got a lot of weak acids. Now, I again do the reverse. I do that twice or thrice, basically to see whether I can remove all these minor contaminants. Okay. And then later in the last step, when I add sodium and potassium hydroxide and I start to concentrate it, now depending on the relative solubility of penicillin salt vis-a-vis the other impurities, which also form what are called as sodium salts, I'll find that since they are at smaller concentrations, I will need to concentrate the water even more in order to let them come out or precipitate come out. So before they can precipitate out, the penicillin will come out. Okay. Now usually this is not the end, although the procedure says, in the end I'll get a sodium salt or penicillin and I'm done. They'll actually check it out to see whether there are other impurities, and many times they might also do column chromatography, okay, to separate penicillin from all the other things. Okay, so it is not as easy as you think. Okay, I do one extraction and I'll get it into the aqueous layer, and why do I do it again and again? Because there are a lot of other components which also will come with penicillin. So I'm trying to remove them by doing this back and forth 2 or 3 times. Okay, is that clear? Hello?
Yes, sir.
Okay, any other question?
Sir, I had a question.
Yeah.
So, you mentioned semi-synthetic penicillin. So,
Correct.
by some mutation, that it can't be prepared itself. Like,
Okay. Some of the semi-synthetic penicillins which we make are so unusual in structure that probably if you try to give those precursor to the penicillium chrysogenum, rather than putting it onto penicillin, it will start metabolizing it to something else. Okay, and therefore you will find that some derivatives you necessarily have to make it in the lab. Okay, some basic ones. For example, as I say, phenoxyacetic acid derivatives or hydroxy phenylacetic acid derivatives, that the fungus seems to be able to put into the main ring, and you get some variety. Okay, but If you look at the number of derivatives penicillin are there in the market, all of them you cannot put as a precursor in the fermentation, because some of them become food for the fungus, and you'll just use them rather than putting it into the penicillin. So yeah, some may, but many times you are unable to, because the derivatives that you wish for and the side chain that you wish for, if you put that precursor, the organism simply eats it up. Okay. Does that answer? Yeah, yeah.
Yes,
So some you can, but many you cannot. Okay. Okay. Any other question? Okay. So if not, can I stop recording? Okay.
Yes, sir.
yes, sir.
So I'm going to stop recording here.